Hello everyone, welcome back to all in this new video. Here we are going to see the validation of STAD RCDC software with the manual calculation, especially for the designing of ordinary beam. So for better understanding, we will go with the multiple pages. So your page first to third will define the model definitions that we are going to set in the ETABS software. Your page 4 will define the analysis results that we are getting from the ETABS software, and page 5 will define how to export the ETABS result for the STAD RCDC. Your page 6 and 7 will define how to set the definition in STAD RCDC software for the designing of the beam element. Your page 8 and 9 will define the flexure and shear design of the proposed beam by STAD RCDC software. And from page 10 to 14, we will see the manual design of the same proposed beam for the flexure and shear, and thereafter we will compare the result of STAD RCDC and the manual calculation. And in the last of this video, I will give you some concluding notes that will define what actually the parameters which is creating the difference between the result of STAD RCDC and your manual calculation. And if you are controlling that parameter, so your results of the manual calculation and STAD RCDC software for the designing of the beam will match. So without wasting time, let's start. So first of all, try to understand the model definition. So here it is a G plus 9 floor building, and the material properties were used as M30 for the concrete and Fe500 as a grade of main reinforcement and Fe415 as a grade of shear reinforcement. So you know very well, IS 456-2000 has limited the maximum grade of steel for the shear reinforcement to as Fe415. So I'm considering that it is in your knowledge. And the section property for this model we have used as beam as 300 by 600, and the columns are of sizes 300 by 700. The loads were considered as 5 kN per meter square as a live load for all the slabs, and dead load as considered as 2 kN per meter square for all the slabs. The wall loads over the beam has been assigned as 10.35 kN per running meter. The load pattern here it is considered as dead, live, earthquake in X direction, earthquake in Y direction. So these are the load patterns we are considered for this model. Now have a look over how I have defined the section property for the beam in the CSI ETABS software. So we have considered the name of the section as beam 300 by 600. So 300 by 600 is the section size of the beam. But the important thing is that I have considered the effective cover for the beam from the top and bottom as 58 mm. So why I have considered it as 58 mm, I will let you know when we are going to design or when we are going to set the setting in the STAD RCDC software for the designing of the beam element. There I will reveal why I have considered this effective cover as 58 mm. So our intention is to match the result of STAD RCDC software with your manual calculation. So this is actually the important parameter that is playing an important role for matching the result of your STAD RCDC with your manual calculation as well as your STAD RCDC software with your CSI ETABS software. So if you would like to compare or if you would like to match the result of the beam amongst all these three, manual, STAD RCDC and the ETABS software, so you should focus on this effective cover, because this effective cover will actually match the effective depth of the beam between your manual calculation, between your STAD RCDC software, between your ETABS software. So this thing you should keep in mind. This is a very important factor. So that's why I have taken the effective cover for the beam as 58 mm. So this thing you should keep in mind. After that, have a look for assigning the earthquake load. What I have considered for mass source, I have considered the factor multiplier as 1 for the dead, and for the live load were considered as 5 kilonewton per meter square for each slab. So IS 1893-2016 has suggested that if your live load is more than of 3 kilonewton per meter square, at that time you have to consider only the 50% of your live load. So based on that codal recommendation, I have considered the multiplier as 0.5. Thereafter, we have assigned the earthquake load in X direction. We have assigned the earthquake load in Y direction. You can see the definition here. As we are going to do the ordinary detailing. That's why the code has suggested to consider the response reduction factor as 3. That's why I have taken the response reduction factor in the ETABS software as 3 for the definition of the earthquake loading. Now, in respect of these different loads as dead load, live load, earthquake load in X and Y, I have defined the multiple load combinations. But while the analysis and the design and validation, we are not going to focus any of this load combination except of this basic factor load combination. So here in our proposed problem, we are going to see the design calculation and design results only for the factored load combination, that is 1.5 multiplied by dead load plus live load. So we are not going to focus on other load combinations which is having the concern of the earthquake loading, right? So we are going to focus only the factor load combination. Keep in your mind. Okay, after performing of the analysis, what we are getting from the ETABS software, here the beam at its end under the factor load combination, we are getting the shear force as 118.19 kilonewton at the end of the beam. This beam is having the span of 4.5 meter. That is very important to understand. And at both of the ends, this is actually the beam we are going to take into consideration. The beam along the grid 3 and between the grid B and C, this beam we are going to take into consideration. So the column here, it is oriented like this. The column here, suppose this is your beam and this is the column which is oriented like this. Okay, your column is having the size of 700. This column is also having the size of 700. So if you would like to know the clear span of the beam, so how much it will become? Total span of the beam is actually 4.5 meter. So 4.5 meter minus 0.35 from this side, 0.35 from this side multiplied by 2. From both of the side we have to consider. If you subtract this 4.5 minus 0.35 multiplied by 2, you will get the value of the clear span as 3.8 meter. So later on, for the further calculation, we will proceed with this span of the beam, which is actually the clear span as 3.8 meter. Remember, apart from that, the shear at the end of the beam, we are getting the maximum as 118.1966 kilonewton. Now at the mid of the span, it is the fixed beam. As you can see at both of the ends, the columns are present. So it is the fixed type of the beam, and you know the fixed type of the beam will have the sagging moment at the mid of the span and hogging moment at its ends. So sagging moment we are getting as 75 kilonewton meter approximately, and hogging moment at both of the ends here as well as here, due to symmetry we are getting the same value as 59.6029. So these are the analysis results for which we have to design this particular beam by STAAD RCDC software and by manual, and then we will see whether the results are matching or not. Now moving forward, so you know very well, if you would like to design any element in your STAAD RCDC software, so your RCDC software is not capable of performing of any analysis. Your RCDC software is not capable of doing the modeling. Okay, in RCDC software you can do the design, scheduling, detailing, everything, but prior to that you need to do the modeling and analysis. So that is not possible to do in your RCDC software. So for that reason, we need to give the data to this STAAD RCDC software for the purpose of designing. So for that reason, I am going to export the result from the ETABS analysis results that we are getting in the last stage. These analysis results we are going to export from the ETABS in the RCDC software. So once you land inside of this RCDC software, so what to do? So very first thing you need to do, that is what? General and reinforcement setting in STAAD RCDC software for the purpose of designing the beam element. So here general and reinforcement setting, we are going to ignore the torsion. Torsion we are not going to consider. Rest of all things we are not going to do the ductile detailing, because we are going to deal with the ordinary beam design. That's why we are going to consider it as what? Non-ductile. Okay. Thereafter, the detailing type we are going to fix it as based fit bottom detailing style. So that is not the concern of the discussion of the today's session. That's why I'm going to skip this part. Actually, the IS code has recommended to consider the minimum percentage of reinforcement. So IS 456-2000 has suggested that minimum percentage of reinforcement, that is what AST, area of reinforcement, divided by effective area B into D, effective depth, that should be equal to 0.85 divided by Fy. If you calculate this ratio, so you will get the value of 0.17. That's why accordingly I have defined here as 0.17 as the minimum percentage, and nominal also we are going to consider the same value as minimum, and the maximum percentage the code has suggested to consider as 4%. So these all recommendations you will see in your manual calculation. I am just giving the idea why we have taken this value. Now importantly, we have to see here the grade of concrete. So the grade of concrete will be M30, grade of steel will be Fe500 for the main reinforcement. So in general, how we are calculating the effective depth of the beam? So suppose overall depth we are having as suppose 600 mm. Okay, for the proposed example we are having the effective depth, overall depth as 600. So in general, if suppose you are going to calculate the effective depth, if I am going to consider the clear cover as 20, shear reinforcement of diameter 8 mm, and main reinforcement is suppose I am going to consider as 12 mm diameter of bar. Okay, so for that reason, if suppose you are going to calculate the effective depth, so what you will do, effective depth will equal to overall depth, that will be 600, minus your clear cover, that will be 20, minus your shear reinforcement as 8 mm dia, then minus half of your main reinforcement, that will be 12 divided by 2. It is a general approach. Suppose this is your beam, and suppose this is your shear reinforcement, and in that you are going to provide the main reinforcement of diameter of bar as 12. So what we are doing, we are calculating the cover up to the center of the main reinforcement. So that will include the clear cover, then diameter of shear reinforcement, then half of your main reinforcement, that I have given here: clear cover, shear reinforcement, half of your main reinforcement. So after doing this calculation, you will get your result. What value you are getting? Let me calculate that. So 600 minus 20 minus 8 minus this will be 6, that you are getting 566. Okay, this is what the actual consideration, actual calculation. But the algorithm of the STAD RCDC software for calculating the effective depth is something different. So here we need to understand what is the algorithm of the RCDC software for calculating the effective depth. For that, you need to understand this thing first. Actually, your RCDC software is not considering directly main reinforcement layer as one only. RCDC software what actually doing, if your section of the beam having the overall depth is less than of 400 mm, so RCDC considered as only one layer of the main reinforcement, and if your depth is in between 400 to 1200 mm, so RCDC considering it as two layers. One layer will be present here, and another layer RCDC is going to consider to be present here. And then accordingly you can see here, if your depths are going to increase with the different ranges, so the number of layers are going to be increased. You can see from here. So actually RCDC is not going to consider the effective cover only up to this extent, the center of this first layer. No, RCDC is going to consider the effective cover at the center of this spacing, this clear spacing between the two bars. RCDC is considering the effective cover here. Try to understand. Here RCDC is going to consider the effective cover up to this level. So what to do? Let's try to understand with example. As per the SP34 page number 100, in no any case the clear spacing between the two layers of the tension reinforcement, this clear spacing between the two layers of the main reinforcement, that should not be less than of 15 mm. That should not be less than of 2/3 of your maximum aggregate size. M stands for your maximum aggregate size, and in no any case it should be less than of the maximum diameter of the tension reinforcement. These three criteria are there. So among these all three, you have to consider the maximum one. So like 15 mm, then 2/3 of the maximum aggregate size, and diameter of the tension reinforcement. So amongst these all three, in most of the cases, most commonly the greater value we will get from this second option. So next, now the general formula where RCDC is following to calculate the effective depth. So RCDC is following this formula for calculating the effective depth. That is what effective depth will equal to overall depth minus clear cover minus D1, the diameter of the maximum reinforcement in the first layer, D1. So this diameter of the bars in the first layer called by the RCDC as D1, in the second layer RCDC is calling it to as D2. So our concern with the D1. Okay, now D is the effective depth, CC is the clear cover. Now very important, clear cover is not just a clear cover by the consideration of RCDC software. Remember, RCDC including the diameter of the shear reinforcement also in the clear cover. If suppose you are going to define the clear cover as what, 20. So RCDC is not considering the clear cover only 20. RCDC considering the clear cover as 20 plus diameter of the shear reinforcement as 8. So suppose it is going to become 28 mm. And due to this reason only, remember, I have defined the clear cover as 28 mm. So hope that you all understood why I have defined it as 28 mm. Now next, D1 is the diameter of bar used in the first layer that I have explained. S is the spacer, clear spacing between the two layers, and that is actually calculated by 2 times maximum aggregate size divided by 3, where M stands for the maximum aggregate size. So as per the RCDC consideration, the value of S in no any case should be less than of 20 mm. Actually, see, RCDC what going to consider, in no any case RCDC is going to compromise with the this S spacer less than of 20 mm. In no any case, if the value after doing this calculation is coming out to be less than of 20, so RCDC is going to consider it as 20. If the value is coming out more than of 20, then the RCDC is going to consider this spacing between the two layers as the calculated value if it is more than of 20. For better understanding, look at this example. So here, example first, where the beam size as 300 by 600, clear cover I am going to consider as 20 and shear dia I am going to consider 8 mm. So maximum aggregate size is going to become 30 mm and diameter of the first layer bar as 20 mm. Now the basic formula for calculating the effective depth by the RCDC is this one. Now S is equal to 2 times maximum coarse aggregate size, here it is considered as 30 mm, divided by 3. So it is the value is coming out to be 20, which is not less than and not greater than 20. It is exactly 20. So if this value is coming out to be less than of 20, at that time you have to consider at least 20. Remember. So by the calculation, see, it is going to become 542. See, what overall depth as 600, 20 plus 8, which is turns into the clear cover minus diameter of first layer. Yeah, very interesting. In every case, RCDC is considering this D1 as minimum of 20 mm. Even if you are going to consider the main reinforcement as 12 mm diameter, even if you are going to consider main reinforcement in the first layer as 16, but irrespective of whatever the diameter you have considered, RCDC is going to consider this diameter as 20 in every case. This is what the important thing you need to know. And now S where RCDC is going to calculate or consider based on this calculation. If the value after the calculation is less than of 20, it is going to consider at least as 20. If the value is coming more than of 20, the RCDC is going to consider that value. So by putting all this value here, we are getting the effective depth as 542. Now next example, where the section size is same, clear cover is same, and shear reinforcement is also same. Now maximum aggregate size I am going to consider as 35. Diameter of bars, again I said RCDC by default is considering as 20 mm. So you don't have a control over this 20 mm diameter of bar for the main reinforcement in the first layer. Now D effective depth. So for that we need to calculate the S. So S will equal to 2 times M divided by 3. So see, by the calculation we are getting the value more than of 20. So obviously software will follow this 23.33. So after doing the calculation, the value of the 540.33, the RCDC is going to consider this effective depth of the beam. If you would like to validate this discussion, you can practice on your own with the STAD RCDC software by playing these two things, clear cover and maximum aggregate size. So here what I have considered 28 as clear cover and 25 as what? As the maximum aggregate size, and our overall size of the beam is what? 230 by 600. So see here, if suppose for our proposed example, effective depth will equal to what? 600. Okay, first we will find out the spacing. Spacing will equal to 2 times maximum course aggregate size as 25. I have taken 25 divided by 3. So how much it is going to become? See, 2 times 25 divided by 3. So we are getting 16.67. So obviously this value is less than of 20. And what RCDC is considering? RCDC is not going to consider this 16.67. RCDC is suggesting that in any of the case, your value should not be less than of 20. At least you need to consider as 20. If the value is coming more than of 20, then you have to consider that. If the value is coming less than of 20, then you have to consider at least 20. Okay, so S is 20. So effective depth will equal to 600 minus clear cover. Clear cover will include your clear cover as I have defined here. Okay, 28. So 20 plus shear reinforcement as 8. That's why I have defined here as 28. So that's why it is 28 minus diameter of first layer. What I said, diameter of the first layer bar RCDC by default considering as 20 minus this S, whatever the value we are getting, S equal to 20, we got the value. So 20 divided by 2. If you are going to do this calculation, let me show you. 600 minus 28 minus 20 minus 10. So we are getting 542 is the effective depth. So later on we will see whether the software means RCDC is calculating this effective depth or not. See here I have set the value of maximum diameter of bar for the main reinforcement as 16, but still RCDC will calculate the effective depth of this one because it is considering the diameter of bar as 20 as default. Even after the design we will decide the main reinforcement in our proposed beam as 12 diameter only. So this should be actually 12, but RCDC is not considering the diameter of bar as 12. RCDC in every case is going to consider this diameter of bar as 20. Remember this point. So we got the value of 542, and if you subtract this 600 minus 542, so how much the value you will get? Definitely you will get the value of 58 That's why in ETABS software, at the time of defining the section property for the beam, I have taken the effective cover as 58. Hope that you all understood why I have taken this 58. So if suppose you want to match the result of ETABS software design result and you want to match the result of STAAD RCDC, so you have to control this parameter of the effective depth, right, and effective cover. After that we have set the maximum number of bars as 4 because we would like to have the sufficient spacing between the bars, longitudinal bars, and if the bar is more than of 20 dia, so 55 spacing we will get. So IS code recommending to have the minimum spacing between the two longitudinal bars. If suppose one bar is laid like this, so the spacing should be minimum of 25. So we are having 60 60, so it's okay, 60 and 65. Next, load cases, dead, live, earthquake X, earthquake Y. So all the load cases here it is considered for the design purpose, but we are not going to design with the earthquake load combination. We are going to design the proposed beam with only factor load combination, basic factor load combination, that is actually present here. The load combination for the designing of the beam by STAAD RCDC 1.5 and 1.5. Okay, dead and live. After that, see, this is the design output by the STAAD RCDC. So beam number 8 we have considered, it is a B30 of the proposed. I said that the clear span of the beam, it is what? 3800, 3.8. Overall span of the beam is I think 4.5. So if you subtract the support from both of the side 0.35, 0.35, you will get the clear span of the beam as 3800 or 3.8 meter. Now width as 300, depth as overall 600. See, RCDC is not giving any calculation for the effective depth. Directly it is giving the effective depth. So what we have calculated the effective depth? 542. So it is exactly matching. Okay, in respect of that I have explained how the algorithm of the RCDC software is working for calculating the effective depth. Okay, later on all the definitions are actually present here. clear cover we have defined as 28 mm, right? Based on that only you will get this 542. Now the design calculation. So bottom and top. So at the middle, because it is a fixed type of the beam, so at the ends we are getting the 59 point something moment, and at the middle as sagging we are getting the moment as 75 under the factor load combination 1.5 dead plus live. So design means torsion we are not going to consider, we are going to ignore the torsion. That's why torsional movement is not there, 0 0. Okay, so we are going to consider at the mid, that is positive main reinforcement at the bottom and negative hogging main reinforcement at the top. So here at the mid, and either you can consider left or right, both will be same. So I'm going to consider mid only and right only. Okay, now 75.05 kilonewton meter, 59.6 kilonewton meter as negative hogging moment. Okay, now based on that mu limiting capacity, that will equal to 0.133 FCK BD square. See, everywhere your effective depth will be important. Your overall depth will not be important that much. Effective depth. That's why we are trying to control the effective depth. So, limiting moment resisting capacity of the beam is 352. Whether it is right or wrong, we will see with the manual calculation. Now, percentage minimum reinforcement percentage we set, we have defined as 0.17% overall the span of the beam. Now, based on this movement, to resist this much movement, how much the percentage of reinforcement is required is 0.203. Whether it is right or wrong, we will see later on. Now at the end, minimum reinforcement is required actually. Okay, because movement is very less, so minimum reinforcement is required. Next, the provided percentage of reinforcement is 0.209. So in respect of for this 0.203, if you are going to multiply with the section size, so we are getting the reinforcement to be provided as 329. Demand of the reinforcement is 329, area of the reinforcement required for this beam, and at the end the area of the reinforcement required as 276. Okay, so these are the demand, but to satisfy this demand we need to provide 3 bars of 12 mm diameter. How these bars are coming we'll see later on. So finally provided area of the reinforcement is going to become 339, and here also if suppose 3 bars are you are going to provide, so it is going to become 339. So at every of the sections the reinforcement areas are same, right? So this is what the flexural design of the proposed beam by the STAD RCDC software. Now the shear design. The shear design is what? See how much percentage of the reinforcement. Obviously for the beam the shear force will be maximum at the end. That's why either you have to consider left end or right end. So here at right end, how much the percentage of reinforcement, main reinforcement available? 0.209. You can see from here 0.209. Right, top and bottom everywhere 0.209, either at top and bottom. If it is different, you have to consider the minimum one. If it is at top, at bottom we are getting 0.209, at top right we are getting 0.209. In any of the situation, if suppose you are getting different value, so at that time you have to consider the minimum one. Okay, remember this point. Now but here no confusion, both the values are same. That's why we are going to consider it as 0.209 percentage of reinforcement, and shear force is 118.2 kilonewton meter. Now torsional shear is not there, that is 0. So final design shear force will be 118.2. Now nominal shear VU upon BD, with this value we are getting the nominal shear as 0.73. We will compare it with the manual calculation later on. Now this is a nominal shear, we have to compare this nominal shear with a critical maximum shear, and we have to compare it with a critical shear. So after doing the calculation we are getting the critical shear 0.34. Okay, so your nominal shear tau v is greater than tau c. So at that time we need to design this beam for the shear. So what is the shear capacity of your concrete? So formula for shear capacity of your concrete VUC, that is equal to tau C B into D. After doing the calculation, the software is getting the value of 55.37. Okay, we will see whether it is right or wrong. Now shear to be resisted by the shear reinforcement 62.83. It is actually present here. So if suppose you want to resist, if suppose it is needed to resist this much shear force, okay, by the steel, so the calculation you need to do, and after doing the calculation, it is needed to provide two bars of two-legged 8 mm diameter of bar at a spacing of 300 mm center to center. Based on that, the shear reinforcement as provided as 335.13 mm square per meter span of the beam. So for a 1 meter span of the beam, how much area of the shear reinforcement is needed to provide? That is what 335.13 mm square per meter. Two-legged 8 mm diameter of bar at a spacing of 300 mm. So whether the RCDC has done the correct calculation and design or not, that we will validate with the manual calculation. So now we are going to start the manual calculation. Now let's start the design for the same beam with the same analysis values for the moment and shear force. But at this time we are going to design this beam manually, and we are trying to match the results that we are getting from this manual calculation with the STAD RCDC results that we have seen just now. Okay, design result by the STAD RCDC are actually present here. Now at the same time we are going to do the calculation manually. So here the moment, that is what the sagging moment at the mid of the span is 75.05 kilonewton meter, and hogging moment, that is the negative moment at the support at the both of the ends, as 59.6 kilonewton meter. You know the shear force value is 118.19 kilonewton at the both ends of the beam. Okay, now the flexural design of the proposed beam, the size of the beam we have taken as 300 by 600 overall. Grade of materials as M30, AP500 and AP415 for the shear reinforcement. Effective depth, as actually we have to match the effective depth with our STAD RCDC consideration. Try to understand. Here the STAD RCDC is having the effective depth as 542. So intentionally I am going to put the values here such that the effective depth should come out to be 542. Okay, so for that reason I have considered as clear cover as 44. 600 is the overall depth minus 44 clear cover minus 8 mm is the shear reinforcement minus half of your diameter of bar. So here initially I am going to consider the calculation with the main bar of diameter as 12 mm and shear reinforcement of diameter as 8 mm, right? So accordingly the effective depth we are getting as 542. So this is only the parameter you should try to keep the same in your manual as well as in your STAD RCDC. Then only it is possible to match the results. Okay, so limiting or resisting movement will become, as we are using Fe500 grade of steel, so the formula coming out to be 0.133 FCK BD square. Effective depth, see importance of effective depth. So 0.133, 30 is the your characteristic strength of your proposed concrete. 542 width of the beam is 300 multiplied by 542 square. So moment of resistance limiting capacity is 351.64, which is more than of both of the movements, sagging movement as well as hogging movement. That's why the beam will be singly reinforced beam. But I want to see whether the RCDC has calculated the correct moment of resistance as 351 or not. So have a look over the RCDC moment of resistance. 351 we have calculated manually and RCDC has calculated 352. Almost both are same. We have calculated as 351.64. So almost it is 352. So yeah, here moment of resistance calculated by manually RCDC is matching. Next, reinforcement at the mid. Longitudinal reinforcement at the mid. So at the mid, how much the moment is available? 75.05. So put all the values in this formula. So we are going to put especially the moment as 75.05. Rest of all things you can see from here. We are finally getting the area of reinforcement required as 329.61 at the mid of the span. So again I am going to check it. The RCDC at the mid of this span 329 we have calculated. What RCDC has calculated the reinforcement required at the mid? 329, exactly matching it is. Try to understand. 329 we have calculated manually and RCDC also calculated 329. So it is what matching. This is also the reinforcement demand at the mid of the span is matching. Now next, ST minimum. So ST minimum, as the IS code has suggested to consider the minimum reinforcement as a tension 0.85 divided by Fy multiplied by B into D. Okay, so for that reason I am going to do the calculation here. 0.85 multiplied by B into D divided by Fy. So after doing this calculation, 276.42 minimum area of reinforcement. Let me check what RCDC is considering the minimum area of the reinforcement. So RCDC is considering the minimum area of reinforcement. Here it is not showing the minimum area of the reinforcement. It is just giving the percentage. Yeah, in respect of this percentage, the software has calculated the area 276. It is 276 in respect of this minimum percentage of reinforcement. Okay, 276. So we also have calculated the correct value. Okay, 276. So this is also matching. ST maximum. So 4% of your section size, overall section size 7200. Right now it is not having the use here. Let it to be as it is. Now percentage of reinforcement required in respect of this demand. So actually you have to compare minimum reinforcement, maximum reinforcement, and you have to compare it with your ST required. So here ST required 329. Minimum is how much? 276. So 329 is greater than this minimum value. That's why we are going to provide 329. 329 divided by B into effective depth. So percentage of reinforcement required. It is actually what required? 0.203. Let me check what RCDC has done. RCDC has calculated point at the mid. Remember, PT calculated. This is the PT minimum. This is the PT calculated at the mid of the span. Try to understand. 0.203. So exactly matching it is. And it is 0.203 according to 0.203. If suppose you are going to provide the reinforcement, that is what 329.61. I am going to provide the main reinforcement of dia 12 mm. So total area divided by unit area. So 2.914 number of bars are required to provide. So obviously this is what odd number of in fraction. So in fraction it is not possible to provide the reinforcement. That's why we are going to provide the 3 number of bars. So 3 number of bars multiplied by unit area. So demand is 329. Actually with 3 number of bars it is going to become 339.291 mm area of reinforcement. So finally this we are going to provide. That's why we need to calculate the provided percentage of reinforcement, that is ST divided by BD. So it is coming out to be 0.209. Let me check it by the RCDC. So RCDC has done the same calculation, and at the mid of this point, see, PT provided 0.209 and 339 mm area of the reinforcement has provided, and 3 bars of 12 mm diameter. So exactly everything is going to match at the mid of this span. Likewise, we are going to do the calculation at the end of the span. Now the reinforcement demand at the end of the beam, that is actually the negative moment. And how much the negative moment we are having? 59.6. So that I am going to put in this AST required formula. I am getting the value as 259.835 mm square. This much area of the reinforcement required at the top over the support. This is in demand. These are the requirement. But I have to compare it with the minimum area of the reinforcement. So minimum area of the reinforcement is 276.42. So 276 is more than of this demand area. So anyhow, you have to provide at least minimum area of the reinforcement. Okay. So for that, I am going to follow this much area as minimum area of the reinforcement going to provide for that negative section for the top face. So ST divided by BD, 276.42 divided by 300, 542. So we are getting the percentage. Obviously that will be 0.17 minimum percentage of reinforcement. Okay, so providing 12 mm diameter of bar as ST is less than minimum, that's why we are providing the minimum area of the reinforcement. So 12 mm diameter of bar we are going to provide as a main reinforcement, as we did for the middle bottom face also. Okay, so 276 divided by 113.097, 2.44 number of bars are required. So that's why I am going to provide 3 number of bars as the negative reinforcement at top face. Hence needed to provide area of the reinforcement as 3 times unit area, 339.291 mm area of the reinforcement. How much the percentage of reinforcement will be? Again, ST divided by BD, 339.291 divided by 300. Effective, always when you are going to find out the A percentage, you have to consider the effective depth, and this value you should multiply with 100. Remember, here it is not written, but you have to multiply it by 100. Here also you have to multiply it by 100, so you will get it in percentage. Okay, here also you have to multiply it by 100, then you will get the value as 0.203. Okay, so I have to compare these all calculations with stat RCDC at the end. So demand is what? 259. Let me see the RCDC. So in RCDC, minimum area of the PT is minimum this one, and calculated will also be the minimum one, because anyhow you have to provide the minimum reinforcement. Okay, so that we are going to provide this much area of the reinforcement, and if you are going to provide the bars, that is going to become 3 bars of 12 mm dia, that is turning into the 339.3 mm square area of the reinforcement. If you are going to calculate the percentage of it, that is going to become 0.209, and everything matches with our calculation. If you remember, as 0.17 minimum, and finally provided 0.209. So overall, an area of the reinforcement is also provided 339 at the end. Let me show you again. 339, here it is what at the end also they have provided by the RCDC, right? So overall, I am going to conclude that the flexural design by STAD RCDC as well as your manual calculations are matching. There is no any difference. Exactly, both are matching. Now have a look over the shear design. So we earlier have seen the shear design by the STAD RCDC. Now we are going to see the shear design by your manual calculation. So I am going to summarize the calculation of the flexure. So at the mid, moment is 75.05, shear force at that section 30.046, and area of the reinforcement provided 339, percentage is 0.209. Now at the end 59.6, but shear force is 118. 118 at the end, we have seen this value. Now 339, area of the reinforcement provided, percentage is this much. So amongst these two, mid and end, you have to see the shear, because you want to design for the shear. That's why you have to focus the maximum shear force among these two. So we are getting the maximum shear this, and at this section what percentage is available? This percentage of reinforcement is available, right? So these two things we have to follow. Remember, this much force and this much percentage of reinforcement has provided. Now after that, the critical location needed to be considered for the design of the shear will be end. At the end we have to consider. Now nominal shear tau v will you VU upon BD, shear force divided by 300 multiplied by effective depth. See the importance, everywhere we have to use the effective depth. That's why intentionally I tried to match the manual calculation effective depth as well as software RCDC effective depth consideration, right? So that's why what we are getting the nominal shear as 0.73. Let me check with STAD RCDC whether it is matching or not. Tau v 0.73, exactly matching. 0.73 at right end as well as left end, both the values are matching. Now next, after this nominal shear, we are looking forward for calculating the critical shear. But before of that, we are calculating the maximum shear 0.63 under root of FCK, that is going to become 3.45. Okay, nominal shear is less than of your maximum shear. If in any case tau v value is greater than tau c max, at that time you need to revise the design, but that is not the case. Here we can proceed. Tau v is less than tau c max. Available reinforcement percentage. Now I just want to know what is the critical capacity of your section to resist the shear. So for that the formula is VU is equal to, due to concrete capacity, tau c B into D. So for that reason we need to calculate the critical shear. For that we need to have the percentage of reinforcement. So how much the percentage of reinforcement available? That is what? 0.209. So in respect of this 0.209, you have to find out the tau c value by following the table number 9, page number 73 of IS 456-2000. So based on available percentage and for the grade of concrete as M30, you need to do the interpolation, because our value of the percentage of reinforcement 0.209. I think it is coming out to be in between 0.15 and 0.25. In between these two value, your percentage of reinforcement is present. So for that, you need to do the linear interpolation and you have to find out the value. So after doing the calculation, you are getting the value of tau c as 0.34. Round of value you are getting what? 0.34. Actually 0.3372. I am going to round up this value as 0.34. Let's match it with your RCDC calculation. It is again matching with RCDC calculation 0.34 critical. Now shear resisting capacity by your concrete section. Tau C B into D. So here it is what? 55.37 by RCDC. So I am going to do the calculation tau C B into D 55.37 where RCDC has calculated, and by my calculation, manual calculation, we are getting the value 55.284. So exactly this one is also matching. Now actual shear force is 118.19 and capacity of the concrete is only 55.284. So net value 62.906 is the responsibility to resist this load by your shear reinforcement, by your stirrups. It is the responsibility, the stirrup has the responsibility to resist this load, or in another way you can say that we have to design the shear reinforcement to resist this shear force. Okay, so for that reason, as per the IS code, the minimum reinforcement, vertical reinforcement, that will be equal to, let me show you here, if you are looking at this figure, shear reinforcement vertical stirrups, that should be 0.87 fy ASV divided by unit area of the stirrups with available legs multiplied by effective depth divided by spacing of the shear reinforcement, and these are shear resisted by your steel. I am going to use this formula for calculating the shear reinforcement. So for that reason 0.87 Fy ASV into D divided by SV. Okay, so put all the values here, especially this shear reinforcement to be resisted by steel. Okay, that I am going to put here. So after doing the calculation, remember ASV by ASV, area divided by spacing, we are getting this 321. This much is the area. I am going to multiply it with 1 meter span. So it is coming out to be 321.4 mm square per meter. This much area of the reinforcement as shear we need to provide. Now minimum shear reinforcement, this is what the demand. What minimum reinforcement? So as per the codal recommendation, what minimum reinforcement should be? So as per the codal recommendation, clause number 26.5.1.6, IS 456/2000, page number 48, minimum shear reinforcement, this much should be. So that I am going to do the calculation here. That is what? 0.4 B divided by 0.87 Fy, 0.4 300 divided by 0.87 shear reinforcement. For the shear reinforcement, we are using the 415 grade of steel. Okay, IS code has limited this much for the shear reinforcement. Maximum grade of steel should be 415. So that's why it is going to become 0.3324 multiplied by 1 meter span. So we are getting 332.4. Now compare this minimum value with this demanded value. So minimum is more than of this demand. That's why anyhow you have to provide at least minimum reinforcement, that is 332.4 mm square per meter. Hence there is need to provide shear reinforcement at least equal to a minimum value that I am going to provide here. Okay, now SV spacing, how much the spacing? So I am going to provide two legged vertical stirrup. Means suppose we are going to provide, as this one is the most common single ring or shear reinforcement, so it is having two legs. One leg, if suppose if I am going to provide 8 mm diameter of bar, so one leg will have the unit area as 50.26 something. So 50.26 multiplied by two legs. So unit area at one section is how much? This much divided by demand of the minimum reinforcement 332.4 over a 1 meter. So what spacing we are getting? 302.4 mm. This much spacing you have to provide. But as per IS 456/2000, the provided spacing in any of the case should not be more than of 300. Your spacing of the shear reinforcement, this suppose the one shear reinforcement, then suppose this is the another shear reinforcement. So the spacing between these two shear reinforcement, that should not be more than of 300 in any of the case. So by the calculation we are getting this value as 302. So you are allowed to provide it as 300 maximum. So we need to close this bar, close this shear reinforcement from 300 to at least this value as 300. So now providing two legged 8 mm diameter of bar at a spacing of 300 mm center to center. That's why if you are going to close the bars, so obviously area will increase. So I am going to do the calculation unit area 2 times 50.26 divided by last time 332 we have taken. Now spacing we are going to provide here as 300. Okay, so it is going to become 335.06 mm square per meter. This much area of the reinforcement we have provided. Now let's check this calculation with your STAD RCDC. So I am going to check it with STAD RCDC what RCDC has done for the shear reinforcement design. So here we are having the shear design. So finally the RCDC has provided the spacing for the provided spacing as 300 mm and total area provided 335.13 mm square area of the reinforcement. So let me show you here 335 we also have calculated provided 335.06 mm square per meter span of the beam. So overall your flexure design as well as your shear designs are matching with your manual calculation and with your STAD RCDC. Now final conclusion of this study is the design result for the flexure and shear are exactly matching as we just have seen for the ordinary beam design between the manual approach and by STAD RCDC approach for the designing of the beam, and it is possible to match the result if you are controlling all the design parameters, especially as in RCDC when you are going to set the settings for the design you have to control the minimum area of the reinforcement. You have to give the proper definition for the minimum area of the reinforcement. First you have to define the clear cover by thinking that clear cover where RCDC is not considering only the clear cover plus shear reinforcement, and also you have to give the predefined maximum aggregate size that what effective depth you would like to consider. So your effective depth is mainly depends on this clear cover as well as this maximum aggregate size that you are going to define in your STAD RCDC. So again I would like to show you in image where you have defined the this all definition in STAD RCDC. So when you come to this page, general and reinforcement setting in STAD RCDC, so you have to control this minimum area of the reinforcement plus clear cover and maximum aggregate size. These two things you should keep in mind how to consider it that we have discussed in detail. So this if you are controlling these things, so your design output will be in your control. And if you are going to do the calculation manually, you need to keep the effective depth as same as that were considered by STAD RCDC in addition to all other parameters like grade of concrete, grade of steel and all. Then definitely your STAD RCDC design results as your manual design results, both the design results will exactly match. Hope that you all understood this complete concept for the designing of a particular beam by manual as well as by STAD RCDC. Welcome you all in ISO certified live training program ETABS, RCDC and Excel that makes you a professional structural engineer. In this training program you will learn everything about ETABS and RCDC from basic to advanced, real life project of medium rise structure from architecture plan to final design sheet, real life project of high rise structure with all advanced topics, design of structural elements using advanced Excel sheets. Have a look over the features of this training. Daily live classes conducted by expert for 1.5 hours. Recording of every session with lifetime access. Can interact with expert anytime 24/7. Exposure to real practice. ISO certification of training completion. It's 5-star rated training program. Till now more than 1,000 participants have benefited from this training program. Now you are the next. Hello everyone, welcome you all in a new ISO certified live training program, design of substructure using CSI Safe, Excel and manual. In this training program you will learn all about the concept of substructure design, commands in CSI Safe software for the substructure design, validation of CSI Safe result with your manual and advanced Excel sheets. This training program will cover 4 real life projects. In the first and second we will cover all the types of isolated foundation in CSI Safe software. In the third real life project we will cover the raft foundation, and in the fourth real life project there will be the coverage of pile and pile cap design of basement wall, and at the end of this training program you will learn how to prepare the final design sheet for the site execution. Have a look over the features of this training. Daily live classes conducted by expert. Recording of every session. Can interact with expert anytime. Exposure to real practice. ISO certification of training. It's 5-star rated training program. Till now more than 1,000 participants have benefited from this training program. Now you are the next.